you. It's about 11 o'clock. This is such a delight to have David Landau as our speaker in the Statistical and Nonlinear Physics lecture series. David will speak on exploring complex free energy landscapes with innovative Monte Carlo simulations. David actually was my professor. He was not my own professor, but he was a professor at UGA when I was a PhD student a long time back. And I never really had the chance to take a course from him because I was in UGA for a very short time, little over 2 years during my PhD. But I was very much, influenced by him, and very fond memories of having him as one of our professors there. So David Landau is a distinguished research professor of physics and director of the Center for Simulational Physics at the University of Georgia. He has over 450 publications involving the development and use of diverse Monte Carlo, spin dynamics, and molecular dynamics methods to study the statics and dynamics of phase transitions. For this work, he was given the Anis Rahman Prize for Computational Physics by the APS in 2016. He has lectured at many summer schools, published multiple pedagogical papers in the American Journal of Physics, and co-authored a widely used textbook on Monte Carlo methods published by the Cambridge University Press. In 1987, this was when I was a student there, he created a workshop series in simulational physics. Next year will be the 34th, and helped initiate similar workshop series in Brazil and in China. For his many outreach activities, he received the Nicholson Medal for Human Outreach from the American Physical Society. I know how important that is, David, because I served in the committee that chose Nicholson in one or 2 years. He served as the chair of the Division of Computational Physics, DComp of the APS, and was chair of the International Union of Pure and Applied Physics. International conference, one second, there's a problem with the recording. Okay, and the IUPAP International Conference on Computational Physics, CCCP 1999. He was also divisional counselor for DComp and served on the APS governing council. He has been named a fellow of the American Physical Society, the senior Gangbao Distinguished Professor at Zhejiang University in China, adjunct professor at Aalto University in Finland, and Mainz visiting professor in Germany. He is a corresponding member of the Brazilian Academy of Sciences and received a doctor honoris causa from Minas Gerais in Belo Horizonte, Brazil. He is currently chair of the C20 Commission on Computational Physics of the IUPAC. David received his PhD in experimental physics from Yale in 1967. So let me just quickly see why the recording stopped. I'm going to try and fix it while you get started.
Oh, do you want me to wait until you can get that fixed?
Let's take a second just to. Oh, it is recording. Okay, let's go ahead. No problem. I think it is recording.
Okay.
You can get started.
Let me go ahead and begin then. As I mentioned to Shantu earlier, I feel a little uncomfortable at the moment since normally I like to walk around in front of the audience trying to engage everybody and sense whether or not I've hit the right tone. And like this, it's impossible to do that. So please interrupt me if there are problems or something that isn't clear.
Absolutely.
Okay. I realize not everybody is a Monte Carlo expert. So after an introduction in which I try and justify why this is an interesting problem, I'll give you some background in Monte Carlo algorithms before giving you some explicit applications and try to give you a little bit of a feel for the performance of these different algorithms, why they're so useful now, why they will be even more useful in the future. Okay. Certainly, there are a number of grand challenges today that deal with the behavior of different types of systems with complex free energy landscapes. Very often, the goal is to try and determine the ground state of a system. For example, the native state for proteins undergoing folding. And here what I've shown is the same protein which can fold into a true ground state or misfold into a state that has almost the same ground state energy, but looks very, very different. And an important example is a prion, which is simply a misfolded protein that causes mad cow disease. And the time that it takes the misfolded protein to unfold and find the true ground state is longer than the time it takes the prion to kill the cow. And of course, there is an equivalent Jakob-Creutzfeldt disease in human beings. Another alternative is a glass, in which you have an ordered state which only has local order, but no long-range order. But as statistical physicists, we're not merely interested in the ground state, we're interested in the thermodynamic properties of these systems. And finding the correct thermodynamic properties at low temperatures becomes very, very difficult. Now, when I was a graduate student, we believed that the scientific method consisted merely of the interaction between experiment and theory. But since then, this has turned into an equilateral triangle where computer simulation plays a very important role equal to experiment and theory. And as you've already heard, I began at this corner of the equilateral triangle. I actually used to get upset with my advisor who wanted me to go to the library and read theory papers, because what does theory have to do with the real world? Well, of course, he was much smarter than I was, and I very quickly learned how important that was. But now all three corners of this triangle should interact. This really is intended to be equilateral, although since I'm giving the talk, I put simulation at the top. A number of years ago, at a meeting in China, a colleague from Europe started talking about the Landau triangle. And I thought he was referring to a symmetry principle of Lev Landau that I hadn't heard of. And all he really meant was this triangle. I started showing this about 1980 as I was talking about simulations at magnetism conferences. And after my talks, the experimentalists and the theorists would argue about whether this was theory on the computer or experiment on the computer, and they wouldn't talk about the results. So I started showing this triangle, and I told them it's not experiment or theory, it's something different. So what do you think of the results? Now I think this is widely accepted. But I would like to add the question at the bottom of this slide. Now supercomputers have very large numbers of cores. So how can we perform simulations making truly effective use of massively parallel supercomputers? But the general question that we want to address is that of complex free energy landscapes in a very broad sense. They occur in many different physical systems, and in some cases, they can occur in systems that are not really physical, but which can be mapped onto problems that look like physical systems with complex free energy surfaces. And today I want to consider examples of each kind of system. So first, let's look at a system that doesn't have a true free energy. This is the traveling salesman problem. I'm looking at a fictitious country which happens to have a perfectly rectangular border. And in this case, a salesman has 50 different clients in different parts of the country, given by the dots in this figure. This is just meant to be a pedagogical example. Usually we're interested in many more cases. Okay? And the question is, in what order should the salesman visit all of these clients in order to minimize the distance, capital D, which is traveled? And the distance D plays the role of the internal energy in a statistical mechanics system. Okay. Well, the simplest solution is what I've shown here. The salesman simply visits the system in a completely random order. This is obviously not a very simple route. How can you simplify the route? Well, again, the simplest way of doing that is to interchange the order in which you visit the system in a random manner. And if by interchanging two cities that you visit in order, you reduce the total length or total distance that you travel, then you accept it. Otherwise, you keep the order as it was. And so here is an example in which I actually perform that type of simulation, and I can reduce the order from length 29 in these arbitrary units to about 9.2. And if you compare the two routes that the salesman has visited, you see that there is a substantial simplification. But is this really the shortest route? In other words, is this the ground state? And several decades ago, Scott Kirkpatrick came up with an interesting idea called simulated annealing. For me, this was also very interesting because Scott and I were undergraduates together, and we each did experimental undergraduate theses in the attic of the old Palmer lab at Princeton. And both of us wound up doing computer simulations. In simulated annealing, you accept the change in the order of the cities that you visit with a probability given by a pseudo-Boltzmann factor. So the probability is given by the exponential of minus delta D over T, where delta D is the distance, the difference in distance traveled. T is a fictitious temperature. You raise the fictitious temperature a bit to induce thermal fluctuations, and then you slowly lower the temperature in hope that these thermal fluctuations will allow you to find a lower ground state. So in the upper right-hand corner, we have done the simplest search for a ground state. In the two bottom figures, I'm going to carry out two examples of simulated annealing, starting from the same high temperature and slowly reducing the temperature. The only difference is that I'm using two different random number streams. These were chosen really quite at random. They're not expected to be particularly good or particularly bad. These were made in a simple Python program. So they're not particularly complicated programs. They're not particularly fast. Was there a question, or was that just noise in the background?
The laundry machine makes such a racket.
I'm sorry, I couldn't hear that if that was a question. I couldn't understand it.
No, sorry, go ahead.
Okay.
Yeah.
So you'll see with two different random number streams, you wind up with two different supposed ground states. They not only look different, but they have different ground state energies. So which one is the true ground state? Well, the one with lower energy. But is it the true ground state? Or would there be an even lower ground state if you made a different run with different random numbers? Well, you don't know. And using simulated annealing, there's no systematic way of determining that. Biochemists have finally discovered simulated annealing and are sometimes using this, but this is the problem that you face with simulated annealing. Now, you heard about the Center for Simulational Physics in the days when I used to get mail, not as email, but in folded pieces of paper called envelopes. I sometimes got email to this address, which I actually sort of enjoyed, but I also sometimes got email to this address, which I enjoyed rather less. Now, many of you know that Wang-Landau has a Nobel Prize, but you probably didn't know that I have a Nobel Prize as well. Unfortunately, mine did not come from Stockholm. Mine came from the undergraduate student body at the University of Georgia, which is in Athens, Georgia. Some 2 decades or so ago, at an undergraduate student award ceremony, they gave prizes to their favorite professors as sort of a faculty roast, and mine was a simulational Nobel Prize for the simulation of outstanding work in physics. They chose the wording quite carefully, and they said it was given with love. I like to think it was. Now, many of you know that there are a very large number of foreign graduate students at American universities, but this year all of our undergraduates were American trained and went through the American system of schools before entering the University of Georgia, and they misspelled the word academy. This could be the source of material for another lecture, but I think that's a lecture for a different day. So let me return to statistical mechanics. This is information that I think everybody knows, but I just want to repeat it so that you're familiar with the nomenclature that I'm using. Here, I'm going to restrict myself for the moment to systems with discrete degrees of freedom, although this is easily extendable to systems with continuous degrees of freedom. If we know the partition function, which is defined at the top of the slide, we know everything about the system, but the sum over all states very quickly becomes impossible to calculate because the number of states becomes huge. Now, the probability of any given state, say the nth state, can be written down very, very simply as the ratio of the Boltzmann factor divided by the partition function. The problem, of course, is I've just told you that in practice, it's almost impossible to actually calculate the partition function. If we can, or if at least we have a good estimate for it, then we know the probabilities of the states. If we can estimate the partition function very precisely, we can get the free energy. And from the free energy, we can calculate all thermodynamic properties of the system. So we've outlined here everything that we would like to calculate and how we can get all of the properties of any model that we want to work with. As an example, let's look at what I call the fruit fly of statistical physics, because anytime anyone comes up with a new method or a new theory, they try it out on the Ising model. One has a simple lattice. For simplicity, I've drawn a square lattice with periodic boundary conditions, and the Hamiltonian includes just nearest neighbor interactions between spins I and j, and the magnitude is given by the parameter j. If j is positive in the ground state, all spins will be parallel. Now, if we want to calculate the partition function for this system, for a large system the number of states is still going to be huge. In the example I've shown here, there are 25 spins, so there are already 2 to the 25 possible states. If we have a 100 by 100 system, that's still only a nanoplatelet, but there will be 2 to the 10,000 states. So instead of trying to actually calculate the entire partition function, we can estimate it using a Metropolis Monte Carlo approach, in which we sample states via a random walk in probability space. Well, how can we actually do that in a simple way? The very simplest approach is what we would call single spin flip sampling. And again, for a pedagogical example, I'll use the Ising model. As our initial state, the end state, we can take any configuration of up and down spins, and we can then attempt to produce a new state, which we will call the M state, by attempting to flip a single spin. This is not always the most efficient way, but it's the simplest, and I'm using that as a pedagogical example. Then we only need the relative probability of the N state and M state. And then the partition function cancels out in the relative probabilities. All we need is the ratio of the Boltzmann factors. The ratio of the exponentials is equal to the exponential of the difference in energies. Any transition rate, which is probability per unit time, that satisfies detailed balance is acceptable. And the one which is most often used is the Metropolis form that I've listed here. Metropolis has his name associated with the method because the author list of Metropolis, Rosenbluth, Teller, and Teller was alphabetical. All Metropolis did was supply the computers. The Rosenbluths and the Tellers were 2 married couples. The wives actually did all of the hard work in programming and running the programs. The men stood around discussing it, looking important. That's a little bit of hyperbole, but more or less how it was actually done. Some of you may know of the last author, Edward Teller, who went on to do something less important called the hydrogen bond after he was finished with this. The last time I looked, there were over 19,000 ISI citations to this paper, and many people no longer even give the citation. They simply say they've used the Metropolis method because it's so well known. The advantage is that it's so simple to implement, and this is the Metropolis recipe. You can choose any initial state, randomly choose a site, and calculate the energy difference that would result if you attempt to overturn that site. Generate a random number uniformly on the interval between 0 and 1, and compare that to the flipping probability. If it's less than the flipping probability, flip the spin. Otherwise, leave the spin in its original direction, count that state again, and go back to step number 2. Now, in this fashion, the initial few states that you generate may not be representative of equilibrium. So you may have to run this for a while until you reach equilibrium. And even when you are in equilibrium, you will see fluctuations, which are typical of what we expect from the fluctuation dissipation theorem. Now, this is for the Ising model. Suppose we have an atomic or a molecular system. The recipe is equally similar, but there we might choose a given atom and attempt to move the atom by a small amount, calculate the energy change that result if we move that atom. The energy change would be determined by the difference in potential energy given by whatever potential is appropriate for that system. And the rest of it follows through. You generate the random number between 0 and 1 and compare it with the flipping probability. So you see that the Metropolis method is simple and it is very general. The problem, however, is if you have a complex free energy landscape, there will be multiple minima and maxima in the free energy, and you can get stuck in a metastable minima. And at low temperature, the problem is this flipping probability may become very small because T is very small, and you can't get over a free energy barrier to get out of the minimum and into the true global minimum. So you need better algorithms.
Excuse me.
Yes.
Metropolis algorithm is just for periodic boundary condition or also for finite, for non-periodic?
It works for any kind of boundary conditions. It is really remarkably general. I showed you the periodic boundary conditions as an example, but I should have explained that it doesn't depend upon that. We've used it for anti-periodic boundary conditions, for skew boundary conditions, for free edges. It's really remarkably general.
Actually, there is an analytic method for finite size Ising model, which is graphical method. Means that if it is not necessarily for infinite system, but also for finite system, and it is analytical. So why still people use Metropolis while there is analytical way of solving finite size Ising model?
That was something that was interesting in order to test finite size scaling theory back in 1976. Today, one would not do this for a simple Ising model, but there are many other systems that cannot be solved analytically, even for relatively small systems. I'm using the Ising model here only for pedagogical purposes, to explain Metropolis for people who are not familiar with it.
I see. Thank you.
We used Metropolis several decades ago, for example, with some people in horticulture who were trying to understand mixtures of particles of different sizes and shapes in producing artificial potting media to grow ornamental plants. And there we were able to carry out Monte Carlo simulations and experiments and compare the two. And those are certainly very, very different from Ising models. But it turned out it actually helped us understand errors that were being made in the experiments. I'm sorry, I interrupted a question.
So Metropolis is not for XY model, means that when in each side there are three states, a spin up, down, and middle, something like that.
No, that's a wonderful question. In an XY model, you would have the same kinds of approach that you would have in the molecular system. In the molecular system, you can move an atom by a continuous amount in distance. In an XY or a Heisenberg model, you can tilt the spin by a continuous amount, not merely flip it. And we have used it in XY models, in Heisenberg models, in anisotropic Heisenberg models, in many different types of systems. So again, because Shantu would not give me 3 hours, I can't show you how you can use these in all different kinds of systems. And I've simply selected a few simple examples. At the very end, I will show you how one of the approaches were taken is even being combined with electronic structure calculations in order to do electronic structure at finite temperatures, combining statistical mechanics and quantum mechanics. So this is really very, very general. but for systems with complex free energy landscapes, Metropolis runs into problems.
I see.
Does that help?
Yes, thank you.
If there are no further questions, let me go on. This again is meant to be pedagogical. The first invited talk I gave on simulations when I was in a mixed experimental simulational state was back about 1972. And there, I rated the performance for my Ising model simulations as 1. And about 25 years later, I was asked in a different venue to give a talk, and I just decided to look at the comparison. And I found that there were roughly 3 orders of magnitude improvement in computer speed by that time. Now, computers had changed, the nature of the architectures had changed, word lengths had changed, so it was difficult to really make a quantitative estimate of the difference. So take these 3 data points with a grain of salt. But if I looked at the relative performance for Ising models, including both simulations and methods of analysis, there were roughly 9 orders of magnitude difference in performance. Notice that most of the improvement came not from the computer that you could access with your fingertips, but came from the computer between your ears. And that's an important point that I want for people to understand, and it's something that I always emphasize to my students. Thinking is most important. So back in 2001, Fuga Wang, my graduate student, and I were looking at an improvement in algorithm, and we came up with an algorithm that we published in PhysRev Letters that we called the random walk in energy space with a flat histogram. And we chose that name because we thought it was perfectly descriptive. However, everybody else in the community decided that they would call it Wang-Landau sampling. That was not our name. But since everybody else calls it that, I'm going to continue using that name. Excuse me, please, for doing it. But that's what you'll find in the literature. Someone even started a Wikipedia page under that name, and it's not us. So the method is also simple, but it takes a different perspective. At the top, we have rewritten the partition function not as a sum over all states, but as a sum over all energies. For example, in the Ising model, the first excited state of a simple Ising ferromagnet would be one in which one of the n spins was overturned. But you can overturn any one of the n spins, so that density of states is degenerate, and it's n-fold degenerate. If the number of spins n is large, then that first excited state is highly degenerate. So you can see very quickly that the sum over energies is a much smaller sum than the sum over all states. G of E is independent of temperature. So if you know G of E, you can determine all the properties at all temperatures by simply reweighting G of E by the Boltzmann factor. The problem is that we don't know the density of states. So we're going to determine it iteratively. And what I show on this slide is the recipe. And the recipe is actually fairly similar to the recipe for Metropolis. We start with an estimate for G of E. And the simplest estimate, which is not a very smart estimate, but it turns out it's good enough, is to estimate that the density of states is 1 for all states. Then we choose what we call a modification factor, F, and the initial value of F needs to be bigger than 1. We chose e to the power 1, It doesn't have to be that. It could be 2, it could be 3. We chose e to the first power because we often worked with a logarithm of f, and then that meant the logarithm of f was 1, and that was simple. Now we randomly go through the system, flipping spins with a probability that is equal to the ratio of the instantaneous values of G. Since G doesn't have temperature in it, you don't get any trapping. Choose a random number between 0 and 1, compare with that flipping probability of the ratio of G's, and decide whether or not you're going to accept the new state or not. And in any case, you then multiply G of E by the modification factor F for whichever state results. You also keep track of a histogram of the states that have been visited. And every time you visited a state with energy E, you just increment the histogram by 1. You continue until the histogram is flat. What do we mean by flat? We simply mean that the minimum value is 80% or 90% of the mean value of the H values of all of the states. When that happens, we stop. We decrease F, for example, by taking the square root of F. So now it's closer to 1. We reset the histogram entries to 0, but we keep the improved values of the density of states G of E. And then we go on. And we keep doing that until F is very close to 1, 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, somewhere around in there. And at that point, we stop and we use that density of states to calculate the properties of the system. Now you'll notice since G of E changes, the flipping probability changes as you go along and it violates the density of states. But at the end, G of E is the exponential of 10 to the minus 8. So it's so close to 1 that for all practical purposes, detailed balance has been restored. But that's why we don't use G of E until the end, when detailed balance has been restored. So this is actually a fairly simple algorithm. And there are now over 1,900 citations to the algorithm. And in less than 5 cases have people had to contact us to get help in implementing it. Now there is a very, very small systematic error that remains, and I pointed this out in 2002. But in almost all cases, the systematic error is less than the statistical error. And if you require more flatness, the systematic error becomes smaller and smaller. And there are other ways of dealing with it. And I'm not going to go into that now because usually the systematic error is so small, but I simply wanted to make you aware of that. Let me actually show you a simple pedagogical example for a 16 by 16 Ising model for which we know the exact result. On the right, we show the logarithm of G of E versus the energy normalized by the number of spins and the interaction constant J. The green curve is the exact answer. The red line is our initial estimate. Remember, we're looking at the logarithm of G of E. And the exact answer, even for this small system, varies by almost 80 orders of magnitude. On the left is the histogram. Well, all of the entries are 0 at this point because we haven't generated any states. What I'm going to do is to show you a simulation for this system, and it's not going to be the best simulation or the worst simulation. It is some typical simulation. Each time the flatness criterion is satisfied, the iteration number increases and F decreases. There's a little hesitation, and you can just follow as the density of states, G of E, approaches the exact answer. I'm only going to show you 10 iterations because this is only meant to be a pedagogical example. And each time the system runs, the density of states gets closer and closer, and the histogram is different at the end of each iteration because we're using different random numbers. At the end of 10 iterations on this scale, you can't tell the difference. Well, let's look at larger systems. And here are results for two larger systems, 32 by 32 and 50 by 50. These were done at the time, these are old data. They were done on a fast 200 megahertz Pentium 1. Today, that's about the size, that's about the speed of an old cell phone. When Fugao brought me these results, I told him, Fugao, you've made a mistake. You plotted the same data sets twice by error. Please make a plot of the difference between the exact and simulated results. And in the inset, you see the difference in the logarithms of G of E. The phase transition is located about where the error is 10 to the minus 5. Again, this would be trivial to do today. Here are results for a 256 by 256 Ising model. This system is so big that you couldn't get exact answers for G of E. We know what the exact answers for the free energy are from Onsager's solution, but not for the density of states. In this case, we broke up the region of energy into different segments, and this shows histogram values for each of the different segments. And we ran each one of these on a different computer, okay? And you can see at high energies, we gave a very large region of energy because this is an uninteresting region. And this large region at low energy was relatively uninteresting. The phase transition region is in here, so we looked more carefully. So this was our first attempt to introduce parallelism, but this is really trivial parallelism, and you can't do this efficiently for a large number of cores. Well, let's ask the question, how well does Wang-Landau sampling work for a real system with a complex free energy landscape? And one of the simplest systems is the Edwards-Anderson spin glass. So it's an Ising model, but now J can be randomly positive or negative with equal probability, and it's inside the summation. This will lead to a spin glass state with frustration and a rough free energy landscape. In addition to looking at the energy of the system, we defined an order parameter Q, which was the overlap of any given configuration with the ground state. And we then actually carried out two-dimensional random walk simulations in energy and in Q. You can carry out Wang-Landau sampling in even higher order dimensions. But this is just an example in 2 dimensions. And here are some results for one configuration of bond energies and an 8 by 8 by 8 system. In the lower right-hand corner, you see at high temperatures, the probability, and these are now canonical probabilities extracted from the Wang-Landau results. For the highest temperature of 2.0, you see what looks sort of like a Gaussian distribution with a peak around 0 order. Well, this is what you expect from such a system at high temperature. But as you lower the temperatures, slowly you start getting interesting, rough probability distributions. If you turn these probability curves upside down, you qualitatively get the free energies of the system. And in the upper two panels, the temperatures are low enough that we had to use a logarithmic scale. At the lowest temperature in the upper left-hand corner, you see that there are 30 orders of magnitude difference in probabilities. You can easily get trapped, turn this over. You'll see there are multiple free energy minima and maxima separated by many orders of magnitude. But here, even with simple Wang-Landau sampling, you were able to explore the free energy landscape. If you get to much larger systems, you have to use something even more sophisticated. And this is what I want to tell you about now, which is something that is newer and called replica exchange Wang-Landau sampling. Now, modern petascale computers have more than 10 to the 5th cores. The top 5 all have more than 10 to the 6th cores. Now, usually, those computer centers won't let you get all 10 to the 6th, but getting 1,000 or 10,000 cores is not so difficult. So how can you use many cores efficiently with Wang-Landau sampling and not just trying to do trivial parallelism? Well, we've introduced a simple and efficient and generic framework with a hybrid algorithm. It was first published in PhysRev Letters, and a longer paper describing more detail followed up in PhysRev E. Let me first give you a brief digression to help you understand the background of this. There is a method called parallel tempering or exchange Monte Carlo or replica exchange that has existed for several decades. These are different names, but it's all the identical algorithm, just proposed by different people. In fact, the very first such proposal was by Geyer in 1991, but he wasn't a physicist. He published in a statistics journal, and nobody in the physics community ever read that. So in '86, Bob Swenson and Zhensheng Wang had proposed a simple idea of partial replica exchange, but it wasn't fully introduced in physics until Fukushima and Nomoto did it in 1996. But they weren't aware of Geyer's work. The idea is very simple. Arrange a number of identical replicas at a series of different temperatures, T1 up to higher temperatures where they increase systematically. Simulate all systems simultaneously, okay? And then at regular intervals stop and attempt to interchange configurations with a probability given by the difference in inverse temperatures of the two configurations and the difference in energies. This is simple statistical mechanics. Okay? And again, you would generate a simple random number between 0 and 1 and compare it with this probability. Now, when you're performing simulations at a fixed temperature, you will wind up getting a more or less Gaussian probability distribution in energy space at that temperature. but you don't know exactly what the width will look like until you do the simulation. So when you choose your temperatures, you don't know ahead of time if the probability distributions will overlap. And if they don't overlap, then you never get any of the switching of the probabilities of the configurations. The whole idea of this is to feed fluctuations from higher temperatures into lower temperatures, but if you choose the wrong T, you don't get replica exchange. In parallel Wang-Landau sampling, that is a replica exchange Wang-Landau sampling, you move from the serial version into a parallel version in which you choose overlapping energy regions. You can force these regions to overlap because you're not choosing temperatures for which the results are unknown, but you know what regions of energies will overlap. Then you perform ordinary Wang-Landau sampling within each window, and then regularly you attempt exchanges between configurations in the different windows, again, using simple statistical mechanics. But now you're not using the Boltzmann factors, but the instantaneous densities of states. So here we have an exchange. In this particular case, if you choose these windows, you see that the states have energies that are out of the range of the energy window of their neighbor. So there can be no exchange. Everything really works extremely well, and you revitalize trapped walkers, and you can generalize it. So here we have 3 overlapping windows, but instead of having 1 random walker in each window, we have 3. So this shows how you can use 9 cores instead of just 3. In addition, the energy windows don't all have to have exactly the same size. So at high temperatures, at high energies where there are lots of fluctuations, you can make the windows big. And at lower energies where fluctuations are smaller, you can make the windows smaller so you can spend more time over each energy range. And then you simply put all of the different segments together using the inverse microcanonical temperature. So an important feature compared to traditional parallel templing is that you can ensure that there is overlap between the replicas at the beginning of the simulation. We can actually make performance measures. One example is the simple Potts model, where you have existing ordered and disordered states for a Q-state Potts model. Here is an example for the 10-state Potts model for a 300 by 300 system. There are almost 15 orders of magnitude difference between the minimum and the maximum of the canonical probabilities. Okay? This was actually used, for those of you who are interested, to study grain growth back in the 1980s, where each of the different grains was given a different Q value and then studied as if it were a simple Potts model. Okay? Well, you can define a performance measure which tells you how many serial samplings would you have to perform compared to the number in this parallel algorithm, where the number of energy windows, H, and the number of random walkers, M, can be varied. And here was an example for the Potts model, where we found by increasing the system size and increasing the number of cores, we could keep the number of CPU hours essentially constant, going all the way up to 400 by 400. And doing a serial Wang-Landau calculation, we estimated or extrapolated would take a few years. We didn't actually do that simulation because it wasn't worthwhile taking a few years of CPU time. So if it was 2 years or 4 years, I can't tell you. But in either case, it's many orders of magnitude more than the few hours that we actually measured using replica exchange Wang-Landau sampling. Now this is weak scaling, where we increase the size of the system so that the amount of work that each core did stayed the same. But we could actually look at strong scaling, and this was performed for a coarse-grained lipid model in the continuum, where the number of cores was varied up to about 200. But the size of the system stayed the same. So the number of particles that each core dealt with became smaller, and communication became larger. So you had the potential for communication thrash. But what we found was linear scaling with the number of cores up to about 200 cores. What was interesting is for balanced energy windows, that is for windows of different sizes. These are the red dots, and for all cases, we performed 10 independent simulations to get error bars. We also got linear scaling, but the slope is greater than 1, which meant that the speed went up faster than the number of cores. And this was due to the replica exchange Wang-Landau, and gave you this huge increase in performance. I want to look at a slightly different problem, which is a biologically inspired problem that looks very trivial, but it's actually extraordinarily difficult because of the complex free energy landscape. This was actually introduced by Ken Dill, who was a biochemist, not a theoretical physicist, although this looks like a model that a theoretical statistical mechanician would have introduced. To simplify the protein folding problem, he put the protein on a lattice. So it's a lattice model, and instead of having 20 different kinds of amino acids, he had only 2, hydrophobic and polar. So all amino acids were mapped onto these 2 types depending upon their hydrophobicity. There are tables of hydrophobicity, and all of those above 0 or below 0 either became hydrophobic or polar. These white bonds are strong chemical bonds that cannot break, and the only interactions are given between the non-bonded gray hydrophobic amino acids or beads. There are no other interactions in the system. But you can have many different configurations of the polymer or protein on the lattice, so there can be many different energies corresponding to the different interactions. And the sequences of H and P's are chosen to mimic real proteins. Now, I've shown this in 2 dimensions because it's easy for pedagogical purposes, but you can define this model in 3 dimensions, where you can have tangled spaghetti type configurations, and you can get all types of entropic entanglements from which the system has great difficulty escaping. So back in the early 90s, we did almost 1 million Ising spins in 3 dimensions. And it turns out doing 100 HP monomers is an incredibly difficult problem because of the complex energy landscape coupled with the entropic entanglements. And in fact, it's been shown theoretically that this is an NP complete problem. Traditional moves are very simple, and I'll show you some, but it turns out that they're not adequate. So for example, just flip the end of the protein, and that gives you a new configuration. Or a kink flip, which moves 2 bonds, would be another simple move for this system. A crankshaft kind of move would involve 3 bonds. but it's been known for many years that if these are all you'll use, the sampling is not ergodic. So you can introduce non-local moves by taking some point on the protein and pivoting the rest of the protein around it. If you include that, the sampling becomes ergodic, but it's very inefficient if you have collapsed proteins because the protein keeps banging into other parts of the protein when you attempt to pivot it. So there are other moves that you can introduce that are non-traditional. So on the left, we have a portion of a protein and I've numbered the monomers. So let's try and move monomer number 2. Now we've broken chemical bonds. That's not allowed. So we have to keep moving other monomers until eventually all of the chemical bonds have been reformed. This would now be a new sample configuration, and this is called a pull move, because we moved monomer 2 and pulled the remainder of the protein along with it. Another type of pull move, and this is all decided using random numbers, is shown on the right, where the entire rest of the protein may have to be pulled through, not just a portion of it. If you have very, very tightly collapsed configurations, instead of moving the beads, you may have to move bonds. So here we've cut some of the chemical bonds. We've shown black lines showing what's cut, and then reform the bonds on the opposite sides of those plaquettes. And then the new configuration showing on the right is very different from the one on the left, where you've had to perhaps recolor the monomers so that you have the same sequence of H's and P's. So here is an example of where we've used Wang-Landau sampling for the HP model in 3 dimensions. Here is a 103 monomer model, which turned out to be impossible to solve numerically using some very, very sophisticated methods. The specific heat versus temperature was extracted from the density of states. This is a single run, but you get the specific heat at all temperatures. The error bars were determined by making multiple independent runs. At the specific heat peak, the protein collapses, but not into the native state. At the shoulder, at lower temperatures, the protein rearranges and gives you the native state with some small fluctuations that disappear as you go to 0 temperature. And you see on the right, the ground state configuration or native state configuration that has a hydrophobic core, and the orange monomers on the outside are all polar. There's no symmetry there. It's not like the Ising model where you can easily see when you have the ground state. And if I gave you this state and the first excited state, you wouldn't be able to see the difference. Now let's ask, what happens if this is in concert with an attractive surface? I'm getting to the age where I might have to look forward to a hip replacement. So what happens when proteins come into contact with a non-organic surface? So this would be just a picture showing such a protein that's been attracted to a surface, and there is a steric wall above it that doesn't interact with the protein. It simply keeps it from wandering off to infinity. The curve that I've shown here is a Metropolis sampling result for the specific heat versus temperature, where 10 to the 8th Monte Carlo trials were used for each run, a different run at each temperature. 10 runs were averaged to give you error bars. This looks like a very nice set of results. The only problem is it's wrong. And these are our results. The problem is that at low temperatures, the system becomes entangled, and the time scales become so long that with only 10 to the 8th trials, you never begin to see the correct results. And these are the correct results that we found using replica exchange Wang-Landau sampling. So what's going on? Here are sample configurations. At high temperatures, the protein is extended. At the peak, the first peak, it collapses and forms a hydrophobic core. At the second peak, it adsorbs onto the surface. But then there is another lower temperature peak where it flattens out on the surface and gives you a new ground state structure with a hydrophobic core, but flattens out onto the structure. And both of these lower temperature transitions, if you will, they're not true phase transitions, but both of these transitions are missed even using high performance Metropolis simulations. And just to finish, I want to mention an application that I've had absolutely nothing to do with, but some of my colleagues at Oak Ridge National Laboratory have. LSMS is a density functional theory approach developed there, and it uses, well, it's basically a quantum mechanical approach to solid state physics, the determination of structure of metallic systems, magnetic systems, but it determines ground state energies. And they've combined LSMS with replica exchange Wang-Landau sampling, in which the atoms are allowed to move around using replica exchange Wang-Landau sampling, and the energies are determined by using LSMS. So you're determining the quantum mechanics for the positions of the atoms where the atoms want to be, not where you think they want them to be. And they perform this for 256 nickel atom systems with 100 energy windows and over 50,000 cores combined with 3,000 GPUs. This was using only about 1/6 of their old Titan supercomputer. And on that, they were already able to get a 2.5 petaflop performance. And of course, now they have a much faster supercomputer, and they've also combined it with quantum espresso. It was underway when I made this slide, but I think it actually has now been implemented. So just to summarize, I've tried to present a generic framework called replica exchange Wang-Landau sampling, which is not only highly efficient, but which is very generally applicable and which can be applied on a multi-core MacBook notebook. One of my postdocs from Brazil has actually done that, all the way through very high performance petascale supercomputers. I think more and more systems with complex free energy landscapes will become important problems for the future. And using petaflop and now exaflop supercomputers, we expect exaflop supercomputers next year. And for that reason, I figured I had to update this and say zettaflops, where one zettaflop is 1,000 exaflops. And then I realized that some of my students will be around long enough that they'll see the next tier. And what comes after zettaflops, I had to look it up, it's yottaflops. So let me acknowledge the hard work was done together with Thomas Vogel, who was my postdoc. He's now at the University of North Georgia. Ying-Wai Li went to Los Alamos via Oak Ridge, and Thomas Wüst is at the ETH in Zurich, Switzerland. I nicknamed us the Gang of Four, and I got blank stares from all of them. I was thinking of the Gang of Four in China, the successors to Mao, who attempted to take over the government. and they were all too young to have realized that, even Yingwei, who was educated in Hong Kong. Let me also thank the NSF, the Texas Advanced Computing Center, Oak Ridge, and the University of Georgia Computing Center. For those of you who want to find out more about advanced Monte Carlo methods, I have a brief advertisement. I know the authors of this book very well. I can highly recommend it. There have been a couple of questions, but I'll gladly attempt to answer any more that you have, and let me thank all of you for your attention.
Well, thank you, and let's acknowledge David for a wonderful talk.
May I ask a question?
Yeah, let's not carry on too many, because I'd like to give other people a chance to ask questions also.
So for any system, we can define J according to, like, if we define J, which is coupling constant, then we can calculate transition temperature for the specific system, and that transition temperature is independent from the size of the system. So it means that analytically, by using Onsager equation, we will be able to calculate transition temperature. So, and it is independent from the size of the system. So then why we need simulation when we have transitions temperature just by having J for the specific system?
These days, experimental techniques have advanced to the point that they can actually study systems that are small enough, and computers have advanced to the systems that they can study systems that are large enough that you really can perform simulations and experiments for the same size systems. So you really can compare those directly, first of all. But secondly, there is now a well-developed finite size scaling theory, which I did not discuss, but which enables you to take high resolution results for a series of finite size systems and extrapolate those to extract the behavior for an infinite system. So as an example, we have studied finite three-dimensional Ising models with periodic boundary conditions with over 10 to the 9th spins, and have estimated the critical temperature with error bars in the 9th significant digit. And in this way, we have been able to make comparisons with tensor renormalization group estimates for the critical temperature, and also with conformal bootstrap estimates for critical exponents. There are no analytical results available for the three-dimensional Ising model. And it is exceedingly important that one have more than one estimate available from numerical or theoretical approximate methods if we are going to try and understand such systems.
Okay.
I think Chandan Dasgupta has a question from IISc Bangalore.
Yes. So I was wondering about this thing called critical slowing down. I mean, if you're using standard Metropolis, then it becomes more and more difficult to simulate the system as you come closer to the critical point. Now, in the algorithms that you discussed, is there something like that? Is there's more difficulty in simulating when you are near critical point?
We do not have the traditional critical slowing down using this method. There will be some slowing down simply due to the increase in degeneracy and the change in diffusivity near the critical point, but we don't suffer from the usual kind of critical slowing down. Now, let me also clarify my remark made a minute ago about the three-dimensional Ising model. Because of critical slowing down, we did not use Metropolis. We used Wolf cluster flipping, which largely, but not completely, eliminates critical slowing down. So there are a very large number of specialized Monte Carlo techniques that one can use. And what I was talking about today with Wang-Landau and replica exchange Wang-Landau are very, very general and generic. They are particularly efficient for systems with complex free energy landscapes. They are very effective in dealing with systems in general, in that you can make one run and get results at all temperatures, or if you include, say, random walks over magnetization and energy of an Ising model, from one run, you can get results as a function of all field and all temperature. But they would not be the most efficient algorithms to use if you wanted to perform very high resolution runs near a critical point. There is something like Wolf cluster flipping would be more efficient.
Okay, thank you.
These are also not restricted just to nearest neighbor interactions. You can include next nearest, third nearest, you can include 3-body, 4-body interactions. All of this is very general. I'm sorry for the interruption. I just wanted to make that point before I forgot.
Sure, sure, thank you. No, I just had one more simple question was, that when we are looking at this polygon models, how do you eventually know that you have reached the true ground state?
You don't. That is always a limitation. And what you must do is perform multiple runs with different random number streams and different initial states. And in general, what you will see is that from running long runs under these different conditions, you will in almost all cases invariably find the ground states. But there is no proof of that. And in fact, from the example that I showed you of the system with a ground state of -58, we very quickly reached a ground state of -57. And all of the other sophisticated methods had only found a ground state of -56. And I went to Germany to give an invited talk, and I mentioned this ground state of -57. And I was told that there was a mathematician who claimed that the ground state should be -58. But he couldn't get any of the thermodynamic properties. Well, I didn't know if he was correct or not, but I was a little disappointed because we had -57. And I flew back home, and before I could say a word, my postdoc said, by the way, in the 4 days while you were gone, the computer found that the ground state was really -58. So it didn't take a year of computer time. Okay? But you can never be 100% certain that you're getting exactly the right answer. You have to be very careful, and you have to test these. And in part, I think my experience as an experimentalist helped me, because one of the things that my advisor used to do when I was doing experiments would be to come into the laboratory and say, okay, now let's heat the system up and cool it back down and perform the experiment again and see if you get the same answer. And that used to annoy me, because these experiments were very, very time consuming. But again, he was a very smart guy, and he taught me how to really be very critical about your own work and not simply accept it immediately, how to poke and prod it to see if what you were doing was really correct. And so we try to be very, very careful in the simulations that we do to see to it that we don't mislead ourselves. But you cannot be 100% certain.
Okay, thanks a lot.
Other questions? I have a question while we are waiting for another question, if I may. There are many nonlinear systems, in particular strongly nonlinear systems, where you find that you don't really have a reachable equilibrium state, even if you wait, incredibly long times. Turns out these systems often have, very large fluctuations compared to typical fluctuations we'd expect in an equilibrium state. So there has been some work on these systems. We introduced these quasi-equilibrium systems some years ago, and from the quantum spin community, there came the idea, well, also from the nuclear community, there came the idea of pre-thermalization. So they are both very similar ideas. But the main point is that you don't get to the equilibrium state, you get to some really messed up high fluctuation states, which seem to be the territory of these strongly nonlinear systems. In weakly nonlinear systems, they're probably there too, excepting they take longer time to manifest themselves. So I was just wondering how to make sure that if you are going to sample these states using Monte Carlo approaches, what would be the right ways of approaching such near equilibrium, if you will, or sort of near equilibrium states?
Well, there are two ways of doing this. One is to steadily increase the length of the runs, and the other is to think about new algorithms. Mm-hmm. Now, there are some systems that have already been probed, starting with things like the non-equilibrium steady state systems, the simple Ising models in a field that were studied several decades ago, and where you could see stripes that form in these systems that never really reach equilibrium, but they reach steady states. Okay? But there are other kinds of systems of the kind that you were talking about, which are more problematical. Now, even in the kinds of systems that I've talked about, one of the kinds of problems that people have looked at is the non-equilibrium behavior, where you study the approach to equilibrium. And in fact, there has been a surprising connection between the non-equilibrium and the equilibrium behavior that you found. But what you're talking about now, I think, is really one of the forefront areas in statistical mechanics as a whole, and that includes simulations as well in these strongly nonlinear systems. And in many of them, there really is no theory and no clear simulation to go on. And this is what makes them so intriguing and so difficult.
Yeah, thanks. No, there are certain structures that you see in these systems, like you alluded to stripes, right? And these structures are not necessarily intuitive based upon equilibrium statistical mechanics, but if you approach them from purely nonlinear dynamics, they may seem more intuitive. But as you said, they're mathematically largely uncharted, so you simulate, you got to make sure your simulations are right. You can only do so much by doing dynamical simulations, by solving equations of motion. So some other smarter way of looking at these many-body nonlinear non-equilibrium systems as they inch towards equilibrium or near equilibrium or get hung up would be really powerful, especially combined with parallel computing, and smarter tools. So it seems like the replica approaches and so on, all these various sampling approaches might potentially be quite useful to get snapshots of these systems at different late times. And once the snapshots begin to match up, you perhaps can make a measure of how close you might be getting to the equilibrium equipartition state.
If you are near equilibrium, absolutely. The interesting cases, however, are when you have very, very big systems. and you don't even know what you're looking for. And they're so big that you can't simply look at them to tell. And this is where machine learning starts playing a completely important role. And particularly cases where you don't have guided machine learning, where you try and have the machine search for and find something where it doesn't know what it's looking for to begin with.
Mm-hmm.
And this is, I think, an extremely important and extremely difficult kind of problems. I can look at even 1,000 by 1,000 Ising square lattice and pick out patterns. But what happens 10 to the 20th particles? There's no way that you can look at that. Okay? And you need some other way of trying to determine characteristic behavior when you have absolutely no idea what that characteristic behavior is or how it's changing with time. So we really need to develop some new tools that simply were not necessary even a decade ago. And there's work that's going on. Whether or not we're working in the right direction is really unclear. There are lots of fascinating problems, and zettaflop and yottaflop computers are going to, I think, reveal even more problems, both in terms of equilibrium and non-equilibrium systems.
Thank you. That's intriguing stuff. Any other questions? Sorry for taking up so much time.
Excuse me, if the system is very big, is it possible to use Kadanoff blocks to reduce it to a smaller size and then simulate it? Like something like renormalization for blocks, like a Kadanoff block, so that we reduce the number of particles or sites of a real system, so that we can run it less expensive. I mean, with doable condition.
Yes, coarse graining of a variety of manners can be used. And Monte Carlo renormalization group, in fact, has turned out to be one of the most effective ways of actually using renormalization group to get actual answers. If you want to deal with very large systems, you have to be very careful about the coarse graining that you do, that you don't lose some of the physics in the process. But don't forget the kind of example that I gave you in terms of the HP model of protein folding is a kind of coarse graining method that has some of the characteristics of what you were talking about. I realize it's not exactly Kadanoff coarse graining by any means, but it in spirit is doing exactly what you were talking about. And in fact, we've actually been able to find the folding funnel that all biochemists like to talk about. And in all of the literature that I have seen, I've seen pictures of rough folding funnels, and the folding funnels always have free energy on the vertical axis and parameter X on the horizontal axis, but they never tell you what X is because they don't know what X is. Mm-hmm. And in this simplified HP model, we've actually found that in multiple sequences, if X is simply the end-to-end distance for the protein, you can actually get a folding funnel that looks just like these pictures in this very coarse-grained model. And we also find that the shape of the folding funnel changes with temperature, and even the location of the minimum changes with temperature. And these concepts I have never seen in any of the biochemistry papers. Now, I'm not an expert in biochemistry, but I think this is something that they have not seen in any of their sort of all atom treatments that we may have learned from the coarse graining. So your idea, I think, is a very good one. The implementation is not altogether trivial, but it's something that one needs to keep in mind.
Could I ask
Okay.
just because I asked a lot of questions?
Let's see if anybody else has a question, because you have asked quite a few. So I just want to also bring it to a close. So let's go around and see if anybody else has a question. Please go ahead and ask. I'll give you a couple of minutes. Okay, go ahead and ask your question, Ali.
I mean, is there any formula or something that, for example, if the size of the system is 5 by 5, then the number of iteration of Metropolis and Monte Carlo should be this much, so that all the lattice sites at least be chosen once, and also enough iteration for the whole lattice, so that we get to equilibrium thermodynamically? Is there some like a number here to reduce the number extra runs for the program?
No, there is no single simple formula, because different systems behave very differently. So you really need to do some preliminary investigation for the system that you're interested in.
Okay, thank you.
Okay, so are there any further questions? If not, let us thank David for a fantastic talk. I don't hear questions. Okay, great.
Well, thank you very much.
This was very nice. Thank you for taking the time. This has been, I think I told the year wrong for your Raman Prize. It was 2002. You said?
I'm sorry?
Your Raman Prize was 2002, was it?
To be honest, I'd have to look it up and see.
Okay, I may have said the year wrong when I introduced you, so my apologies for that.
I wouldn't worry about it. Thank you so much for the invitation, and thank you everybody for your attention.
Thank you. Really loved it.
Bye-bye.
Have a great day. Bye-bye.